Okay, then let's start. Uh, Firstly, I am Hyungjun Yoon, one of the class TAs who will support you during the third project of implementing the virtual memory. So today, I'm going to introduce the brief introduction about the third project and some background knowledge about it, which is centered on paging. So firstly, we have some announcements regarding the project information. So inside this project, you have to implement 5 different types of functionalities. So the first thing is paging, especially the demanding paging. And the stack growth. The current Pintos has only one page for the stack, but you have to enable the stack growth to enable the larger stacks. And the memory map files, and accessing the user memory and larger page support. And as the previous projects, you have to submit the design document that explains about your implementation. It has no points, but you will have some disadvantage if you don't submit it. And the details grading criteria that we are going to use for the grading will be same as the output file after making the file with make grade inside the VM directory. So please refer to that. You have 1 month for the implementation. So the deadline for the project is November 28th. And unlike the previous projects, it has a little bit larger portion for the total grade. So 40%, it'll take 40% of the project grade. And we also have made the project document and some needed files or materials for the project, such as the patch file. So please go to the link provided here. And the design document is also attached there. Please note that before you start the project, I strongly recommend to read the project document from the bottom, and it will make the project much more easier. And you can use Git for the collaboration with your teammate, but make sure that you make it private so that the other students cannot access there. And no late submission is allowed. And here's one other important thing. So you have to implement your project 3 based on your implementation of project 2. So it means that after you implement all the things in project 3, your implementation should pass all the test cases of project 2. So here's the submission link, and please follow the guided format here for the submission. So for the lab session, we have 3 topics for this project 3. The first thing is paging, and the second thing is stack growth and the memory map files. And in this lab session, we'll only cover the paging, and in the later lab session, we'll cover the other topics. So let's start with the paging. Here, we have the figure representing the address space of the current Pintos. So as you can see, it shows the relationship between the virtual address and the physical address. And in the virtual address, we have some very familiar regions like stack, IPSS, data, and text region. Note that here, we don't have the heap. Actually, in Pintos, we don't have the heap region, so you don't have to care about it in the implementation. And in the actual systems, the virtual addresses are not directly mapped to the same value in the physical address, since it is virtualized. And what takes the role of translating the virtual address to the physical address is the page table. And note that that kind of page tables structure depends on the hardware structure, so that our Pintos is based on the x86 hardware structure, so that it uses the 2-level page tables, so that it doesn't have a one structure, but has the page directory and the page table pages. Note that. And one other thing you can watch here is that there are some memory regions inside the physical memory that are mapped to the real disk space, and that only exist inside the memory. So we call the memory spaces that only exist in the memory as the anonymous page, and the other pages that has the mapped region inside the disk as the fileback page. You have to separate them inside the project. So what does the current Pintos do? Before the implementation of the virtual machine, it directly maps the virtual page to the physical page. So the entire executable files is loaded at once at the beginning. So it's quite inefficient. So in this project, you have to make it more efficient by using the virtual mapping the functionalities between virtual pages and physical pages, and by using the demand paging. So here are the very big level instructions of the things you have to do inside the project. Firstly, enable the demand paging. So do not map the pages when the program is loaded, but when it is needed. And then the pages does not only exist inside the memory, but it can be replaced with the swap space inside the disk. And then enable the stack rows. Currently, we only have a 4 kilobyte page for the stack region in the Pintos, but you have to enable the growth and implement the memory map files. So before this project, the method how you access the memory was like using the write and read system functions. But using mmap, you can directly access to the memory space for the writing or reading. So you have to implement this function and enable accessing user memory for the process that you're using. So today we'll focus on how to implement demand paging and some required things that you have to understand for the implementation. So basically, we have the two different kind of structures named virtual page and virtual page frame. So both are composed of 32 bits. And inside the 32-bit, they're divided into 20-bit of page number or frame number, and the others are the offsets. So the page number are usually used to look up the starting point of the real page. And then using the offset, you find the real page. And then what the page table does here is mapping the virtual page number to the page frame number. Actually, as I said before, it is defined depending on the hardware structure. And since Pintos is based on x86, it uses the fixed structure of the two-level page tables. And you can use the internal APIs which is related to the page table functionalities. And you don't only have the mapped frames inside the physical memory, but they can be replaced or evicted to swap space. So you have to also implement this. And then, as I said before, the real frames can be divided into two different categories. The first thing is which is only stored inside the memory, and which is mapped to the file inside the disk. So I guess this will also be covered inside the class. So when we execute the code, usually the text and data are fixed inside the use the physical memory that has the fixed region inside the file. And for the BSS stack heap, which is usually initialized later or written later, we have the memory space. We have the in-memory frames which is named as anonymous pages. And for the mmap, it is usually mapped to the file inside the disk. But actually, when you call the mmap function, if you don't specify a file descriptor parameter there, actually that mapped region can only exist inside the memory. So please note that. So after you understand the concept of this kind of virtual pages and page frames, you would wonder what to implement inside the Pintos code. So you can start from the function named pageFold inside the userproc exception.c. So to briefly introduce what it does is when we access the virtual address and there doesn't exist the translated page frame that is mapped to the virtual address, the pageFold function happens. And what the current pageFold does is it just kills the program. So here you can see the kill F here. But in this project, you have to remove this line and replace this with the proper functionalities for the virtual space. So what you have to do, here are the things for the basic instruction. Firstly, you have to check whether the accessed virtual address is valid or not. So what we mean by invalid virtual address. If it is not a user address and only accessible by the kernel, you have to kill it. And if it at the same time, if it is not a valid user address, you have to kill it. And if you don't have if it doesn't have a proper permission, you also have to kill it. So if the address itself is valid, what you have to do is you have to allocate a proper frame for that. And then if needed, load a file or load the swap disk, or just simply initialize it as an all-0 region. And then after allocating the frame, you have to map the frame number and the virtual number into the page table entry. And we have a function, we provide a functionality for that. So yes, that is all. And one thing to check here is that, so if you want to get the full point, you have to implement the shared pages. So different kind of processes can access to the same page if they refer to the same thing. So that in that case, if the page frame is already allocated, and if you initialize another program, then the page frame might already exist in the page table. So not in the page table, sorry, in the physical memory. In that case, when you for the page table entry that maps the new program's virtual address and the existing page frame, you have to consider that. And so the basic thing you have to care about was the virtual page numbers and the physical frame numbers. But there are some additional information that you have to care about. So as I said before, there are some read-only files and writable files. So you have to manage the permission of them, and at the same time, the type of the virtual pages. So as I said before, there are some ELF files and general files and the swap area. Why do you think we need to differentiate the type of the file? So in this case, in the example of the swap area, actually it only exists inside the physical memory without the mapping with the disk, so that you can modify it. But for the other two things, it is not modifiable since they are fallback page. So in that case, if you simply just divide the type of them, you can manage the permission between them and prevent some accidents by writing some unwritable files. And yes, of course, for the physical memories that has the reference to the file, you have to specify that. And you have to also specify the amount of the data in the page. So usually all of the pages have the fixed size of 4 kilobytes. But if you think about the page that indicates the last part of the file, then it might not be 4 kilobytes. So you have to indicate the rest amount of it. And if it indicates the swap area, you have to make a pointer to the location of the swap area. And for the in-memory frames, you have pages, you have to make the in-memory flag. So it is the very, very abstracted structure representing the functionalities you have to make. So if the program accesses a virtual address space, what it does is, using the page table, it finds the proper physical frame inside the physical memory. And if there does not exist a proper frame there, page fault occurs. And in that case, what you have to do is allocating that empty frame and then loading a page from the file disk inside that frame. And for that, so how to implement that? There's one method that we recommend by defining a data structure named VM entry. So it's a kind of abstracted data structure to help your implementation. So as I said before here, we need to define a lot of additional information to manage the functionalities inside this project. So if you just define a data structure named VM entry here, and as the attributes of the VM entry, if you define all of the needed attributes, the implementation should be much more easier. So this is the same as the figure that I have shown from the starting of this presentation. And the only difference is that we attach the data structure using the VM entries here. So here, when you access the virtual memory, then what we do is we define a mapping virtual memory entry that is mapped with the virtual address. And using that entry, we store all the needed attributes there. And using the attributes inside the information, we map the physical address and the needed permissions or the file or the offset like that. And to manage all of the entries, we have a lot of recommendations to define them. So we need a structure to manage, so like a pool managing all of the entries. And as the pool, you can use different kinds of structures like table, linked list, and hash table. But in this lecture, what we recommend is hash table, as it has the much more clear structure compared to the others. So here's the example of using the hash table to manage that virtual memory entries. So what hash table does is, using the key, we can find a unique entry that is mapped to that, so that if we use hash table, we can set the keys as the virtual address that is mapped to the virtual memory entry. And if the thread accesses to not the thread, if the program accesses to a proper virtual address, then inside the hash table, we find the virtual memory entry using that address. And using the information inside the entry, we can find the page frame or the location inside the disk and the permissions. So here's the recommendation for the implementation. Inside the page, we recommend you to define a structure for representing this VM entry. So all of the attributes that in the previous slides should be here. Of course, the most important things would be maybe the virtual address and the mapping functions and the information related to the files. And then using all of these VM entries, so you will allocate the VM entries once we have the access to specific virtual address. You have to make a data structure that manages all of the VM entries. So for that, our recommendation is making a structure inside the thread structure, since all of them are managed by the single thread. Making a structure named VM, and in this case, we use the hash data structure. So using the keys, we can access each of the VM entries. So it's quite obvious thing. So for initializing and destroying that data structure, what you have to do is, inside the user process.c, is all of the initialization functionality happens inside the start process, so that the VM hash table that manages all of the VM entries should be initialized here. And it should be destroyed on the exit function of the process.c. And for regarding the functionalities of making some VM entries, there are two things that you have to care. The first thing is load segment, and the second thing is set of step. So it is for loading the code segments or the text segment of the program and the initial step for the program. So as I said before, we already have implemented functionalities for them. For example, for the stack, what the current Pinterest does is it just allocates the one single 4 kilobyte page for that. But if you think about the new implementation you have to do, what you have to do is just replacing your own page structure using the VM and VM entry inside the functionality. So yes, what you have to do is allocate the VM page table and make sure that all entries are invalid at the initialization stage, since you have to implement the on-demand paging. So each of the pages should be actually loaded when they are demanded. And we can give you some example of the load segment functionality. So for loading the code region inside the physical memory, what the current Pinterest does is it just allocates the page and loads the data at the first time and sets the page table directly. But now what you have to do is, as I said before, we'll manage all of the information related to the VM using the data structure named VM entry, and we will manage the entries using the VM. So just create the VM entry and insert inside the VM hash table. And when initializing the VM entry, set up all of the needed attributes for that entry for the initialization. And yes, insert the VM entry to the hash table. So it's just replacing all the existing functionalities with a new structure. It's quite simple. So here's the detailed code here. So if you look inside the load segment functionality in the process.c, there are some implemented functions related to this part. So just remove all of them and replace them. And for the stack, actually, the thing you have to do is exactly the same. The current, so yes, the current stack functionality is defined as, sorry, I think that there should be added X here. I will modify the PPT later. So just replace the existing page allocation and page table setting and the setting of the stack pointer as creating a VM entry and initializing the VM entry and adding the VM entry inside the VM table. And actually, later I said that inside this project, you have to implement the stack growth. But in this lecture, we are not going to cover that. And in the later lectures, we'll cover the details. So yes, it's also the detail about that. And it is the overall structure showing the most basic thing you have to do. So again, thread has the maintained VM table. It's a hash table. And when there happens an access to a virtual address, we find the VM entry inside the table. And if the mapped page frame does not exist with the VM entry, the page fault occurs. And what we do next is doing the proper thing when no page, no frame exists with the accessed frame. So in that case, inside the handle MM fault, what you have to do is loading the proper segment from the disk, inside the frame. And after setting up the actual frame, please make the map between the page frame and the virtual address inside the page table that is supported. So actually, to register the kind of mapping inside the page table, you can just easily use an API named install page. It is already defined in the Pintos. So you can just insert the threshold number and the page frame entry there. So here's the summarization of the things, of the implementations that you have to do. Firstly, implement page fault inside exception.c. So again, it happens when there doesn't exist the proper space for the virtual address. So in that case, what you have to do is removing the killing function in the current Pintos, and then replace it to a handler that handles all of the needed functionalities of allocating a new frame and loading the page from the disk to that frame, and then mapping the frame and the virtual address. So delete and implement this part. And it is the figure representing what part you have to replace. So not replace, but newly implement. So when page fault occurs, check whether the address is valid, whether it is a user address or kernel address, or whether it has the right permission. And if it is, please make a VM entry and allocate a new page for that and the load file from the disk to the physical memory, and then set up the page table by using the install page function with the virtual address and the page frame. And here are the details that you have to implement inside the page fault functionality. So I said that it would be much more easier to define a handler that handles all of the needed functionalities. So there are mainly three things. Firstly, allocating a new frame, and then inside the disk, loading the proper page to the frame, and then installing the relationship between the frame and the virtual address inside the page table. So all of them should be inside the handle manifold. So like loading file and install page. So this is also the example of so the diagram of the functionalities you have to implement inside the page fault handler. But note that this diagram only represents the loading the ELF file. So for covering the anonymous different type of pages like anonymous page and fallback page, there are different kind of attributes you have to care, and they'll also be covered in the later lab sessions. So please note that. And yes, actually, loading file is not also supported with the default functionalities, but you have to implement it. So in this case, inside the real physical memory, you have to load the proper file, proper page inside the disk to the frame. So if you check the parameters of there are two things, the address and the VM entry. So as I said before, using the VM entry, you have to manage all of the needed attributes. And actually, the information related to the file, such as where the file exists inside the disk, or some offsets or the permissions are also stored here. So using the information here, you can load the file and then allocate into the virtual, not the virtual, into the frame. And note that if it is end of the file and you fail to write all of the 4 kilobytes of the page, please fill the address as 0. It's really important to get the full point. So it is a diagram representing what you have to do regarding the load file. So firstly, inside the VM entry, you have the virtual address. And using the functionality of the page table, you can find the proper frame for that. And then in VM entry, you have all of the information related to the file and the offset from where you have to read the file. And you can find what to read and load from the file to the real physical memory. So just find the region and load it by using the function of read bytes inside the physical memory that is found with the virtual address and the page table. So yes, it's just one slide summarization related to the functionalities regarding the page fault. Please firstly just make the overall structure inside the page fault, and then make the handler for that. I think the order here is interchanged. Implement a handler to which manages the workflow of the things you have to do. And inside the handler, what you have to do is loading the file and installing the page with the organized information. So note that in this project, we don't provide any kind of skeleton code. So there only exists a directory named VM. So you have to, actually, in the user directory, the files for exception exist, and the skeleton code such as the page fault already exists. But for the data structures such as the VM entries and some functionalities related to the pages, you have to make it by yourself from the bottom. And you have to make them to be compiled with the makefile by adding this kind of line. And there are some things that you can do for testing. So there exists a timeout for the tests, but it might be too tight for you. So what we are thinking is increasing it to 120 seconds. So while testing, please increase the number here, and yes, make the test cases much more easier. And it's not a required thing, but some functions that might help your implementation. So it's just a kind of, what should I say, just a guideline for the implementation. So you have to manage all of the VM entries using VM. So you might need some function named VM init, which initializes the hash table, and VM destroy, which destroys all the things. So when you destroy that hash table, you have to make sure all of the allocated VM entries to be freed. And inside the table, you can define some functions like insert and delete specific VME from that. And yes, the hash function would be the function to put the VM entry inside the hash table. And yes, comparing two different kinds of hash elements and removing memory of the VM entry. So I said that it is only about the demand paging and the basics of paging. And if you implement all of them, I guess that you can implement the later implementation much more easier. And if you want to check whether the basic paging is implemented inside your pintas, you can check it by performing make check here. So there are several test cases, but if you finish all of the things required in this slide, maybe 28 of 109 tests found to be failed, but the others should be success. So you can check it through this. And the appendix is to introduce the functions that you are going to use as the API that is already implemented inside Pinterest. So as I said before, so all of the contents here are, I think you'd be aware of this. So using the function name install page, by giving the virtual address and the real virtual address and the real frame, you can set up the kind of mapping information inside the page table. So yes, it is the thing, one thing you have to know. And for getting a new page and freeing an existing page, you can use the existing functions named palloc get page and palloc free page. And please be aware of the parameters inside there, such as the flags representing whether it is the memory space from the user space or the kernel space. And yes, of course, you have to make use of the most basic functionalities of allocating and freeing the memory. So actually, this is all for the introduction of VM. And as I said before, I also have implemented Pintos when I was undergraduate, and it was one of my hardest course project because of VM. And so my recommendation is firstly, fully understand the structure of how the page table and the relationship between the virtual memory and the real physical frame works. And if you make the full understanding of that, I'm sure that based on the understanding, if you're just implementing it with the very clear workflow, it should be much more easier. So most of the informations are written inside the document. Please read it first and then start the implementation. And do you have any questions related to this? I share things. So the most important about the page sharing is, I think, yes, where's the slide? Yes, here. Is when you, so inside the page fold, I said that if there doesn't exist a page frame inside the physical memory, what you have to do is loading the page from the disk and then allocating the frame and mapping the frame and the virtual address, right? But if we assume a shared page, the page in the physical frame might already exist, since the previous process might have initialized that frame inside the physical memory. So in that case, if you execute a new process and access the physical frame that is already initialized, then the workflow might be changed. So in the page fault, what you have to do is using the virtual address, you map a physical frame and then load the page from the disk, but this already happened. So what you have to do is check whether this already exists, and then just mapping the existing page frame and the new virtual address inside the page table. So that's the thing you might have to care the most about the page sharing. And there's nothing that comes to my mind directly with that for the implementation. But if you start thinking about from that, I guess that you can just implement it properly.
Yeah.